Good morning, friends. After the discussion of the different form of the first law of thermodynamics for isothermal process and at constant pressure, we are going to discuss about the specific heat capacity and also the specific heat. And also we are going to discuss about the molar specific heat. Now first, what is the specific heat or the heat capacity of a substance? Already we discussed about that as the amount of the heat is supplied to the body. So what's happened? The some part of the heat supplied is used to change the internal energy of a system and remaining part is used to do the work on the system. Right? Okay. Therefore, the definition of the heat capacity of a substance is that the ratio of heat supplied delta Q to a substance to the change in temperature of a substance. As we supply the delta Q amount of the heat to the substance, so as a result, suppose the temperature of this substance is increased by delta T. Therefore, the ratio of delta Q to the delta T is known as the heat capacity of a substance. That is known as heat capacity of a substance. Again, what is the heat capacity of a substance? The ratio of supplied heat or the heat supplied to a substance to the change in temperature delta T is known as the heat capacity. It is denoted by capital S. It is denoted by capital S. From definition, the heat capacity is equal to heat supplied to the change in temperature. Again, heat capacity is the ratio of heat supplied to the change in temperature. Therefore, capital S is equal to delta Q upon delta T. SI unit of heat capacity is delta Q is measured in joule or the Kelvin. Joule or Kelvin. Delta T temperature is in Kelvin. Therefore, SI unit of heat capacity is joule per Kelvin or Kelvin per Kelvin. Kelvin per Kelvin. Now, the heat capacity depends on what? So we know that to increase the temperature of or to boil the temperature of water, we have the two container. In one container 1 kg water, in second container 10 kg water. We want to boil this both water. That means to increase its temperature from room temperature to the 100 degrees centigrade. So amount of the heat required for both cases are also different. Right? Okay. That means the heat capacity depends on the mass of a substance. Suppose we have the two substances, one is of copper and second is of other material. Having the both has the same mass. Both are kept at the room temperature. To increase the same temperature of both substances having the same mass but the different material. So in that case also the amount of the heat required are also different. Therefore, the heat capacity depends on the type of material or the nature of the material of a body, and also it depends on the mass of a body. It is mass of a body. Again, so that is the most important for 2 marks question. Define the heat capacity and specific heat capacity. Right? It's SI unit and on which factor both depends. So first we discuss about the heat capacity. The ratio of heat supplied to the body to the increase in temperature is known as the heat capacity. It is denoted by capital S. From definition, the heat capacity is equal to heat supplied to the increase in temperature or the change in temperature. Therefore, capital S is equal to delta Q is the amount of the heat supplied and change in temperature is delta T. Therefore, capital S is equal to delta Q upon delta T is the equation of heat capacity. SI unit of the heat capacity is joule per Kelvin or Kelvin per Kelvin. The heat capacity of a body depends on the material and mass of the body. For different material of a body, the amount of the heat required is also different, and also the two bodies having the same material but the different masses, the amount of the heat required is also different. And due to that reason, for different bodies having the different masses but the same material, the value of the heat capacity is also different. So in short, heat capacity is the ratio of heat supplied to the change in temperature. It is denoted by capital S. Capital S is equal to delta Q upon delta T. SI unit is joule per Kelvin or calorie per Kelvin. It is depends on nature of material and also the mass of a body. Here this, okay. After that, here we shown that the heat capacity depends on the mass of a body and also material of a body. Yet we consider mass of a body is unit, that means the 1 mole or the 1 kg mass. At that time, what is the heat capacity is known as the specific heat capacity. It is known as specific heat capacity. Now, next question is that what is the specific heat or the specific heat capacity? That it says SI unit and on which factor does specific heat depends. Now, the specific heat is defined due to dependence of heat capacity on mass. By using this concept, the heat capacity depends on the mass of the body. We are using this concept to define the specific heat. Therefore, the definition is that heat capacity per unit mass of the body is known as the specific heat of the body. Heat capacity per unit mass of a body is known as the specific heat of the body. Again, the heat capacity per unit mass of a body is known as specific heat of the body. It is denoted by small s. Therefore, small s, that means the specific heat capacity is equal to heat capacity per mass of the body. Suppose the mass of the body is m, therefore, small s, specific heat capacity, is equal to heat capacity delta Q upon delta T divided by m, that means the delta Q upon m into delta T. That is the equation 1. That is the equation of specific heat capacity. Again, the heat capacity per mass of a body is known as specific heat capacity of the body. It is denoted by small s. From definition, the specific heat capacity is equal to heat capacity divided by mass of the body. Therefore, S is equal to delta Q upon M delta T because the heat capacity is equal to delta Q by delta T. That is divided by M. Thus, we obtain specific heat capacity small s is equal to delta Q upon M into delta T. Now, SI unit of specific heat, joule per kg into Kelvin. Now here, SI unit of the heat capacity is joule per calorie, joule per Kelvin, joule per Kelvin, divided by the mass. Mass is measured in kg. Therefore, joule per kg into Kelvin, or the calorie per kg into Kelvin. Again, the SI unit of the specific heat capacity is joule per kg into Kelvin, or calorie per kg into Kelvin. Now, specific heat depends on what? Heat capacity depends on two factors. One is the mass of a body, second is the nature of material. From this, we consider the mass of a body is unit. Therefore, specific heat capacity depends only on the nature of material of the body. The specific heat depends on nature of material of a body. SI unit is joule per kg into Kelvin, and specific heat depends only on the nature of material, while the heat capacity depends on mass and nature of material. They both are similar, but in case of a specific heat capacity, they are divided by the mass. That means the heat capacity per unit mass of a body, that is known as specific heat capacity. And therefore its equation is delta Q upon M delta T. M is the mass of a body, SI unit is specific heat, is joule per kg into Kelvin. Specific heat capacity depends on nature of material of a body. Nature of material of a body. Okay. That is in case of a solid. Suppose we consider the substance is 1 mole. So the heat capacity of substance having the mass is 1 mole, that is known as the molar specific heat capacity. Now we are going to define the molar specific heat capacity. Now the heat capacity per mole of the substance, 1 mole of the substance, is known as molar specific heat capacity of a substance. Again, what is the molar specific heat capacity? Heat capacity per 1 mole of the substance or per mole of the substance is known as the molar specific heat capacity of a substance. It is denoted by C. It is denoted by C. Therefore, C is equal to heat capacity upon number of mole. S, capital S upon mu. Therefore, delta Q upon mu delta T. Mu is the quantity of a gas or the mole, number of mole. SI unit of molar specific heat is joule per mole into Kelvin. Joule per mole into Kelvin. Again, SI unit of molar specific heat capacity is joule per mole into Kelvin. It is also independence of the mass of a substance or the amount of the substance. It is only depends on the material of the substance. Material of the substance. So keep in mind that the easy definition, heat capacity is the ratio of heat supplied to the change in its temperature. It is denoted by capital S. Therefore, heat capacity is equal to heat supplied to the change in temperature. Therefore, capital S is equal to delta Q upon delta T. SI unit is joule per Kelvin or the calorie per Kelvin. The heat capacity of a body depends on the mass of the body and nature of the material of a body. Nature of the material of a body. After that, what is the specific heat capacity? So specific heat capacity is the heat capacity per unit mass of the body. Specific heat is the heat capacity per unit mass of a body is known as the specific heat capacity of the body. Again, the heat capacity per unit mass of a body is known as the specific heat of a body. It is denoted by small s. While the heat capacity is denoted by capital S, here the specific heat is denoted by small s. From definition, so here heat capacity upon mass of the body. Therefore, small s is equal to delta Q upon M into delta T. SI unit of specific heat is joule per kg into Kelvin. Joule per kg into Kelvin. The specific heat of a body depends on the nature of material of a body. It is independent of mass of the body. It is not depends on the mass of the body. Now, what is the heat capacity for the body having the mass is in molar? Is in mole. Okay, heat capacity per mole of the substance. If we consider the substance, quantity of the substance in mole. So at that time, the specific heat is known as the molar specific heat. Heat capacity per mole of the substance is known as molar specific heat capacity of a substance. It is denoted by C. Therefore, C is equal to heat capacity upon the quantity of a substance in mole, or the numbers of mole. Therefore, delta Q upon mu delta P. C is equal to S upon mu is equal to delta Q upon mu into delta T. That is our second equation of molar specific heat capacity. Now, the SI unit of molar specific heat capacity is joule per mole into Kelvin. Joule per mole into Kelvin. It is depends on nature of material and also independent of the amount of substance. Clear this? So there is the two type of the heat capacity. One is the heat capacity and second is specific heat capacity and molar specific heat. So there is the most important question. Combinedly both are asked all. Sometimes there is also asked like to this way. State the difference between the specific heat and state the difference between the heat capacity and specific heat capacity. Clear? Okay. Now after that, obtain the molar specific heat of solid by using law of equipartition of energy. By using the law of equipartition of energy. Already we discussed about the law of equipartition of energy. That means the energy of a molecule substance corresponding to its possible independent motion. The energy associated with its possible independent motion is half kBT. The energy associated with possible independent motion of the molecule is half kBT. That is the law of equipartition of energy. On the basis of the law of equipartition of energy, we are going to define or obtain the molar specific heat C. Right? For that purpose, consider solid of n atoms and each vibrate about its mean position. Here we consider the one solid. In this solid, there are the n numbers of the atom. And according to the temperature, these atoms are oscillate about their mean position randomly. Right? In one dimension, an oscillator has the average energy is 2 into half kBT. Here, the atoms of the solid only perform the vibrational motion. So here the two possibility either horizontal or the vertical. So two independent motion is possible. And according to the law of equipartition of energy, the energy associated with each independent motion is half kBT. Therefore, in one dimension, an oscillator has the average energy is 2 into half kBT. So 2 represents the possible independent motion into half kBT to cancel only kBT. Only kBT. In 3 dimensions, the oscillator has an average energy. In 3 dimensions, it has the 3 different type of the motion along the x-axis, y-axis and z-axis. Therefore, in 3 dimensions, the average energy is 3 times of this. That is in 1 dimension. Now in 3 dimensions, 3 kBT. Again, in 1 dimension, the average energy of an oscillator is kBT. We discussed this way. Now in 3 dimensions, so average energy of the atom is 3 kBT. Clear? Okay. Now for a mole of solid, the total energy is equal to average energy into number of atoms in 1 mole. Number of atoms in 1 mole is equal to Avogadro number. Therefore, average energy is 3 kBT into NA. Now, for 1 mole of solid, the total energy U is equal to the base energy of one atom in 3 dimension 3 kBT into number of atom in 1 mole is equal to Na. But we know that Kb into Na is equal to universal gas constant. Therefore, U is equal to 3 RT. U is equal to 3 RT. Therefore, du by dt is equal to 3R. Take the derivative with respect to the temperature. Therefore, du upon dt is equal to d by dt of 3RT. 3R common. dt upon dt is 1. Therefore, only 3R. That is our equation number 1. Now, from first law of thermodynamics, delta Q is equal to delta U plus delta W. Right? But at constant pressure, work done delta W is equal to P into delta V. Already we derived it. Again, at constant pressure, because here we consider the solid at the room temperature and atmospheric pressure. Therefore, only the change occur in volume of the solid. Therefore, delta W is equal to P delta V. That much work done. Therefore, delta Q is equal to delta U plus P delta V. But in a solid at room temperature, as the temperature changes, the volume of a solid, the change in volume of a solid is very, very small. That means we consider the delta V is equal to 0. As we consider the delta V is equal to 0, therefore delta Q is equal to delta U. Delta Q is equal to delta U. Okay. Now, from the definition of the specific heat capacity of 1 mole of solid, molar specific heat, C is equal to delta Q upon mu delta T. Mu is equal to 1. Therefore, C is equal to delta Q upon delta T. So, from this equation, delta Q is equal to C delta T. Delta Q is equal to C delta T. Here the delta Q is equal to delta U, and here delta Q is equal to C delta T. Compare these two equations. Therefore, C is equal to C delta T is equal to delta U. Instead of the delta Q, we substitute this value. C delta T is equal to delta U. This value. Therefore, C is equal to delta U upon delta T. C is equal to delta U upon delta T is the specific heat of 1 mole. Is the molar specific heat. But already we have delta U upon delta T is equal to 3R. Therefore, C is equal to delta U upon delta T is equal to 3R. Therefore, C is equal to 3R. That is the molar specific heat of solid on the base of law of equipartition of energy. On the base of law of equipartition of energy. So, very easy. Again, consider a solid of n atom and each atom vibrating about their mean position. Now, in 1 dimension, an oscillator of the atom has the average energy is 2 into half kBT. In 1 dimension, the possibility of the independent motion is 2. Therefore, 2 into half kBT, that means the kBT. Here the kB is the Boltzmann constant. Now, in 3 dimension, the average energy of an atom is 3 kBT. Is 3 kBT. Now, for 1 mole of solid, the total energy is equal to average energy into number of atoms in 1 mole. Average energy is 3 kBT. Number of atoms in 1 mole is Na. Therefore, 3 kBT into Na. Therefore, 3 RT. Because the kB into Na is equal to universal gas constant R. Now, take the derivative of this total energy with respect to temperature. du upon dt is equal to 3R. That is the equation 1. Again, we consider the solid of n atoms, each vibrating about their mean position. Therefore, in 1 dimension, the average energy of each atom is 2 into half kBT is equal to kBT. Now in 3 dimension, the average energy of oscillator or the atom is 3 kBT. Right? For 1 mole of solid, the total energy is equal to average energy of 1 atom into number of atom in 1 mole. Therefore, 3 kBT into Na is equal to 3 RT because the kB into Na is equal to R. Take the derivative with respect to temperature. du by dt is equal to 3R. Now, from first law of thermodynamics, delta Q is equal to delta U plus delta W. Now, at constant pressure, the work done delta W is equal to P into delta V. But for solid, the change in volume delta V is equal to 0. Therefore, delta Q is equal to 0. Therefore, delta Q is equal to delta U. Again, from first law of thermodynamics, equation of first law of thermodynamics, delta Q is equal to delta U plus delta V at delta W. But at constant pressure, the work done delta W is equal to P into delta V. Substitute here. Therefore, delta Q is equal to delta U plus P delta V. Okay. Now for a solid, change in volume delta V is equal to 0. Therefore, here we consider the delta V is equal to 0. Therefore, delta Q is equal to delta U. Now, from the specific heat of 1 mole of solid, so C is equal to delta Q upon mu delta T. Mu is equal to 1 mole. Therefore, C is equal to delta Q upon delta T. Therefore, delta Q is equal to C into delta T. Substitute this value of delta Q in equation 2. Therefore, C delta T is equal to delta U. Therefore, C is equal to delta U upon delta T. But we have the equation 1, delta U upon delta T is 3R. Therefore, C is equal to 3 into R. 3 into R. So, there is the molar specific heat of solid by using the law of equipartition of energy. Clear it?